Hello! In this video, we are going to discuss an alternative approach to defining the natural logarithm function. Now, this approach is kind of a weird one, and at the end of the video, I'll give more details about where this approach is discussed. But anyways, to start, let's get an intuitive picture of what's going on. We're going to consider the graph of y equals 1 over x. We're going to say that 1 is right here, and we're going to consider an arbitrary positive real number x. And just for the sake of illustration, we're going to say that x is bigger than 1. We'll say that x is right here. Now, from experience, you probably know that the area under the curve from 1 to x is precisely the natural log of x. And actually, what we're going to do is we're going to approximate the area under this curve using rectangles. So, to do that, we're going to split up the interval from 1 to x into a bunch of sub-intervals. And to see how we do that, well, let's consider an arbitrary positive integer n. And for shorthand, we will denote xn to be the 2 to the nth root of x. And we divide the interval from 1 to x in the following way. Right? So our division is as follows. We start at 1, and next we go to xn, then xn squared, then xn cubed, and you keep going, all the way up to xn to the power of 2 to the n, which is equal to x. So let's just plot each of these guys on the x-axis, right? And we keep going, and eventually we reach x, which is xn to the power of 2 to the n, right? And before that, we'll say right here, we have xn to the power of 2 to the n minus 1, right? So as you can imagine, we have split up the interval from 1 to x into 2 to the power of n subintervals. And now, we approximate the area under this curve using rectangles. And first, let's consider the upper sum, which is going to be the sum of the areas of these red rectangles. The upper sum I'll denote by capital S of dn, and now we're going to add up the total area of all 2 to the power of n of these rectangles. For the first rectangle, the width is xn minus 1, the height is the output value of the function at this point, which is 1 over 1. And for the second rectangle, the width is xn squared minus xn. The height is the output value at xn, which is 1 over xn, and so on. So we're adding up all the areas, and actually we have 2 to the power of n terms in this sequence, because we're adding 2 to the power of n rectangles. But notice, each of these terms are exactly the same. Right, the first term is just xn minus 1. The second term, if you simplify it down, it's also xn minus 1, and keep going. All the terms are xn minus 1. So we're adding 2 to the power of n of them. So the sum of all these is just 2 to the power of n times xn minus 1. And in other words, this is just 2 to the n times the 2 to the nth root of x minus 1. So now we're going to consider the lower sum, which is going to be the sum of the areas of these rectangles, right? The rectangles that I'm drawing in blue. So the sum of the areas of these rectangles up to the blue lines. And I'll denote the lower sum by little s of dn. And so let's figure out the sum of the areas of these blue rectangles. For the first rectangle, the width is xn minus 1. The height of the rectangle is the output value at xn, which is 1 over xn. As for the second rectangle, the width is xn squared minus xn. The height is the output value at this point, which is, we have xn squared, so 1 over xn squared. And we keep going. So we are adding the area of all 2 to the power of n blue rectangles. And actually, each of these terms are exactly the same, right? If you simplify them down, this is really just 1 minus 1 over xn. This is just 1 minus 1 over xn, and so on. And since we're adding 2 to the power of n of them, this sum is just 2 to the power of n times 1 minus 1 over xn. In other words, we have this. So this is what we get for the upper sum. This is what we get for the lower sum. Now remember, the upper sum is an overestimate of the actual area under the curve, while the lower sum is an underestimate of the actual area under the curve. But what happens if we make n bigger and bigger and bigger? What if we let n go to infinity? Well then, we might expect this sequence to decrease to the actual area under the curve, natural log of x, and we might expect this sequence to increase to the actual area under the curve, which is natural log of x. And that is essentially the idea behind this alternative approach to defining the natural logarithm function. So we expect these two sequences to converge to the natural log of x. In particular, we expect this sequence to increase to the natural log of x and this sequence to decrease to the natural log of x. Now, remember, in our diagram, we are considering an arbitrary positive real number x. And actually, in our diagram, we restricted to considering the case x is greater than 1. But actually, we get a similar thing happening if we consider x to be less than 1. The situation is slightly different, but in any case, if x is greater than 0, we expect these two sequences to converge to the natural log of x. This sequence increases to the natural log of x, this sequence decreases to the natural log of x. In fact, in a previous video, we proved that a similar sequence to this one converges to the natural log of x. In particular, we proved that the sequence n times nth root of x minus 1 converges to the natural log of x. But this is just a subsequence of this, right? Because the n's are replaced with 2 to the power of n. So yeah, this guy must converge to the natural log of x. But you know what? Let's forget about the natural logarithm function. Let's forget about the exponential function. The claim is that these two sequences converge, and they converge to the same value. From there, we'll define the value that they converge to be the natural log of x. That is the alternative definition that we're talking about here in this video. And it's kind of strange, because why are we using powers of 2? Why would we do that, right? But in any case, I'll discuss more details about this approach at the end of the video. So we expect these two sequences to converge, and in fact, converge to the same value. And to prove that, let's first note, if x is equal to 1, then we're done. Because these two sequences are constant sequences of zeros in that case. So of course they converge to 0, right? So when we define the natural logarithm function, we have natural log of 1 is equal to 0. So yeah, if x equals 1, then there's nothing to prove, right? There's nothing, it's not interesting. They both converge to the same value because they're constant sequences of zeros. So for the duration of our work, we're going to be assuming x is not equal to 1, because that's where things are interesting. So to prove that these two sequences converge and converge to the same value, it suffices to prove 3 things. We want to prove that this sequence is a decreasing sequence, this sequence is an increasing sequence, and the limit of their difference converges to 0. So we're going to prove these 3 things. If we can do that, then that's enough to say that these two sequences converge and furthermore converge to the same value. So let's first prove that this sequence is a decreasing sequence. And to prove that, what we're going to do is we're going to prove for all n, the nth term of the sequence is bigger than the nth plus 1th term of the sequence. So to prove that, let's give ourselves an arbitrary n. From here, we are going to show that the nth term is bigger than the n plus 1th term. And to show that, that's equivalent to showing that the nth term minus the n plus 1th term is bigger than 0. So let's write out the nth term minus the n plus 1th term. Now, we're going to factor out 2 to the n from these two guys. And if we do that, we get this. Next, let's just drop the parentheses here. And here we'll distribute the minus 2 across this parentheses. So we get this. And then if we just clean this up, we have this. Now, the thing to notice here is, in the parentheses, this is something of the form a squared minus 2ab plus b squared, which we know in general is just a minus b squared, right? So, recognizing this, we have that this guy is equal to this. And now, since x is not equal to 1, certainly the 2 to the n plus 1th root of x is not equal to 1. So we have something not equal to 1 minus 1. So the guy we have in parentheses is non-zero. Well, a non-zero real number squared is bigger than 0, so this guy must be bigger than 0. So yeah, we have shown that the nth term of this sequence minus the n plus 1th term is bigger than 0. And that's enough to say that this sequence is a decreasing sequence. Right, so this proves the first claim. Now we're going to prove that this sequence is an increasing sequence. And so to prove that this sequence is increasing, what that means is we want to prove for all n, the n plus 1th term of the sequence is bigger than the nth term. So let's give ourselves an arbitrary n. And now we are going to show that the n plus 1th term is bigger than the nth term. To show that, it suffices to show that the n plus 1th term minus the nth term is bigger than 0. So let's write out the n plus 1th term minus the nth term. So we have this. So now we're going to factor out 2 to the n. So we have this. Now let's distribute 2 across this parentheses, and we'll distribute minus 1 across this parentheses, so we get this. And then if we clean this up, we get this. But then the thing to observe here is that we're again in the form a squared minus 2ab plus b squared, right? Which we know is equal to a minus b squared. And so we can re-express this guy as this. And now, since x is not equal to 1, we know that the 2 to the n plus 1th root of x is not equal to 1. So certainly 1 divided by that is not equal to 1. So we have a number not equal to 1 minus 1. So the guy inside the parentheses is non-zero. And we know a non-zero number squared is bigger than 0. So this quantity must be bigger than 0. And so we have shown that the n plus 1 term minus the nth term is bigger than 0. So that tells us that this sequence is an increasing sequence. So our claim is proven. Okay, and so now we've shown that this sequence is decreasing. We've shown that this sequence is increasing. Now all that's left to show is that the difference between these two guys converges to 0. So let's show that. So we want to show that the limit of the difference between these two sequences converges to 0. And actually, I'm just going to replace 2 to the nth root of x with the notation we were using earlier. I'm going to replace it with xn. So xn is just shorthand for the 2 to the nth root of x. So how do we show that this sequence converges to 0? Well, the way we're going to show it is we're going to show that this sequence is squeezed between two sequences which also converge to 0. So to see how we can do that, well, let's consider an arbitrary n. And now we're going to re-express this guy in a different way. So let's write out the nth term of the sequence. And what we're going to do is we are going to factor out 2 to the n. If we do that, we get this. And next I'm going to drop the parentheses here, and I'm going to distribute the -1 across this parentheses. And so combining the -1s together, that's just -2. And now we're actually going to combine these all into a single fraction. And if we do that, we're going to write xn as xn squared over xn, write 2 as 2xn over xn, plus 1 over xn. So now we can combine these guys to a single fraction. I'm just going to move over here. What do we get? We get this. But again, notice the numerator is in the form a squared minus 2ab plus b squared, which we know is equal to a minus b squared. And really, the numerator is nothing but xn minus 1 squared. So we get this. But clearly, this guy is greater than or equal to 0. In fact, it's not equal to 0, because since we're assuming x is not equal to 1, that tells us the 2 to the nth root of x is not equal to 1. So we have something not equal to 1 minus 1. So the guy in the parentheses is a non-zero real number. And we know a non-zero real number squared is bigger than 0, right? So this entire thing is actually strictly bigger than 0. So what we have shown here is, given an arbitrary n, we have that the nth term of the sequence is bigger than 0. In other words, every term of the sequence is positive. So now let's think about what we know so far. We know that this sequence is an increasing sequence, and this sequence is a decreasing sequence. Now, since this sequence is an increasing sequence, let's imagine starting at the n equals 0 term, which is just this. As you can imagine, we keep going until we reach the nth term, whenever that is. And then after that, we have the n plus 1th term. But, as you can imagine, this guy must be less than the n plus 1th term of this sequence. Because that is exactly what we've just proven. We have proven for all n, the difference between these two guys is bigger than 0. This statement works for all n, so in particular it must work for n plus 1. Right? And so that's precisely what this is telling us. Right? But then since this sequence is a decreasing sequence, this guy must be less than the nth term, which is this. So you can imagine we start at the n equals 0 term of the sequence, which is that. Right? So this is essentially how we can think about what's going on so far. This sequence is increasing while this sequence is decreasing. The whole goal is to prove that their difference converges to 0. That's essentially what we're trying to show. And notice the n equals 0 this term is nothing but 1 minus 1 over x. The n equals 0 term of this sequence is nothing but x minus 1. Remember, our whole goal has been to show that this guy is squeezed between two sequences that converge to 0. Well, we have one of those sequences, just a constant sequence of zeros. So now, to see what the other sequence can be, well, remember, we just showed that this guy is equal to this guy. So then, what can we do with this? Well, the trick is to multiply both the numerator and denominator by 2 to the n. Right? So we have this. But then we can re-express the numerator as... So we have this. And notice we have 2 to the n times xn minus 1 squared. And what we're going to do is we're going to get an upper bound for the guy in the numerator. So how can we do that? Well, according to what we've established here, we know that 2 to the n times xn minus 1 lies between 1 minus 1 over x and x minus 1. So we know that this inequality is true. And actually, we can use this inequality to get an upper bound for the term in the numerator. And to see how we can do that, well, we have the general property regarding real numbers. If we are given a is less than b is less than c, then that implies either b squared is less than a squared or b squared is less than c squared. And to see why this is true, well, let's just quickly prove it. Right, the whole goal is to prove either b squared is less than a squared or b squared is less than c squared. Now, if b squared is less than a squared, then we're done. So let's assume b squared is greater than or equal to a squared. Well then in that case, if we subtract b squared to the other side, we have a squared minus b squared is less than or equal to 0. In other words, we know that a squared minus b squared is equal to a minus b times a plus b. So we have a minus b times a plus b is less than or equal to 0. But a minus b is less than 0 because a is less than b. So if we divide a minus b to the other side, that's going to flip the sign of the inequality. So we get a plus b is greater than or equal to 0. And therefore, if we subtract a to the other side, we have b is greater than or equal to negative a. And now we see that both b is greater than or equal to negative a and b is greater than a. Now since b is greater than a, well that implies b is greater than or equal to a. And remember, the absolute value of a is equal to either a or negative a. So no matter what, we have b is greater than or equal to the absolute value of a, which is greater than or equal to 0. And so we have 0 is less than or equal to b, which is less than c. And this implies b squared is less than c squared, which is exactly what we wanted to prove. So yeah, that's the reason why this is true. So now we're going to use this in our proof. And to see how we can, well really, this inequality is nothing but a less than b is less than c. And the numerator is just b squared. And we know by this fact that either b squared is less than a squared or b squared is less than c squared. In other words, either this is true or this is true. But no matter which one is true, 2 to the n times xn minus 1 squared must be less than the maximum of these two guys. And from this, it follows that this guy must be less than this guy over 2 to the n xn. Now next, all we have to do is control the xn in the denominator, right? The xn in the denominator, we know, is nothing but times 1 over xn. So what we're going to do is we're going to get an upper bound for 1 over xn. Because if we can do that, that will give us a sequence which converges to 0, right? So we will have that this sequence is squeezed between two sequences which converges to 0. But now, how do we get an upper bound for 1 over xn? Well, we consider two cases. Either x is between 0 and 1, or x is bigger than 1. If x is between 0 and 1, then when we take the 2 to the nth root of x, it's only going to make it bigger. But it's still going to be less than 1. And so, if we take the reciprocal of all three of these guys, it'll flip the sign of the inequalities, so we get 1 over x is greater than 1 over xn, which is greater than 1. And importantly, we have 1 over xn is less than 1 over x. Now in the case x greater than 1, well, if we take the nth root of x, it's going to make it smaller. But it's still going to be bigger than 1. And so if we take the reciprocal of all three of these guys, that'll flip the signs of the inequalities, right? But most importantly, we have 1 over xn is less than 1, right? So one of these two inequalities must be true. No matter which one is true, we always have that 1 over xn is less than the maximum of 1 over xn 1. So this must be true. And because this is true, we have that this guy must be less than this guy. Right? And we've shown this is true for an arbitrary n. So now we see 0 is less than this guy, which is less than this guy. And so what this means is we have shown that this sequence is squeezed between two sequences which converge to 0. Right? We know that constant sequence of zeros converges to 0, and clearly this sequence converges to 0, right? Because it's a fixed number divided by 2 to the n. So by the squeeze theorem, this sequence converges to 0. And so that proves our final claim. And so we have proven all the information that we needed to show that these two sequences converge, and in fact converge to the same value. And so the definition is for each x greater than 0, the natural log of x is defined to be the limit of these sequences. And throughout our work, we were assuming x is not equal to 1. And as we went through that, we saw the following inequalities. We saw this. And really, this sequence is an increasing sequence. This sequence is a decreasing sequence. In fact, the n equals 0 term of this sequence was 1 minus 1 over x. The n equals 0 term of this sequence is x minus 1. So we have this. And we know that this sequence is increasing to the natural log of x, while this sequence is decreasing to the natural log of x. So essentially, we know that natural log of x is somewhere like right here. And so we get the inequalities 1 minus 1 over x is less than natural log of x, which is less than x minus 1. So this inequality is true if x is a positive real number not equal to 1. If x is equal to 1, then all of these guys are equal to 0. So yeah, this is essentially an alternative definition of the natural logarithm function. And from here, you can actually prove the natural log of x times y is equal to natural log of x plus natural log of y. You can prove that natural logarithm function is strictly increasing. You can prove it's continuous. You can prove that the limit as x approaches infinity is equal to infinity. The limit as x approaches 0 is equal to negative infinity. You could prove that the natural logarithm function is onto. So since the natural logarithm function is both strictly increasing and onto, that tells us that the natural logarithm function is 1-to-1 and onto. So the natural logarithm function has an inverse. And so then you would define e to the x to be the inverse. You get e to the x times e to the y is equal to e to the x plus y, and so on. Right? You can go through that same sort of construction process, deriving the usual properties of the natural logarithm function, like we've done previously where we derived the properties of the exponential function. Now it's interesting because it uses powers of 2. We defined another function by the limit of a sequence, which also uses powers of 2. And that function was the arctangent function. Right? If you recall, we defined it as follows. Let x be any real number and consider the following sequence. Well then, we have proven that the sequence 2 to the n xn converges. And we defined the value that this sequence converges to be the arctangent of x. And actually, we proved that another sequence like this one also converges to the arctangent of x. And that was the sequence 2 to the n xn over square root of 1 plus xn squared. In fact, in the case x is greater than 0, we saw that this sequence is increasing to the arctangent of x, while this sequence is decreasing to the arctangent of x. So we have this, but really, the n equals 0 term of this sequence is nothing but x over the square root of 1 plus x squared. The n equals 0 term of this sequence is nothing but x. So we have this. And remember, this sequence is increasing to the arctangent of x, this sequence is decreasing to the arctangent of x, so arctangent of x lies somewhere about right here. And so what we see from this is that x over the square root of 1 plus x squared is less than the arctangent of x, which is less than x. So we've discussed two unusual definitions for two familiar functions. And we see they're both based on powers of 2, and we see really similar consequences. Now this approach is due to Hudowitz, right, German mathematician, and he wrote a paper which discusses this definition of the natural logarithm function. And he discusses more in detail the properties you get from it, and he also discusses this definition of the arctangent function, and some of the consequences. He also mentions some generalizations you can make out of this sort of approach. And I'll leave a link in the description below to the paper, and the paper is actually in German, just so you know. But yeah, it's kind of a weird definition, but I thought it was interesting, so I wanted to share it. And yeah, that's pretty much it for this video.